Hi, my name's Christopher J. Ward from the Kansas University Medical Center, and today we're going to be discussing how to Western blot for polycystin-1 using a monoclonal 7E12. So, Western blotting for polycystin-1 has proven kind of difficult, and it's taken us several years to really perfect a technique that works consistently, and that can be used to visualize polycystin from exosomes, from transfected cells, from non-transfected cells, and from tissue. So 7E12 is a monoclonal antibody that I myself and Albert Ong developed in the Peter Harris lab in Oxford in the late 90s. And it's a really good antibody. So what we're going to do is we're going to do a Western blot of human polycystin-1, but we need some special reagents, and I'll just delineate some of them at the moment. So we're going to use a new page trisacetate gel. I'm going to run that nice and slowly, and then we're going to use a transblot turbo RTA transfer kit. This is a kit that contains nitrocellulose and a transfer buffer, and it's designed for a Biorad gel transfer system. Now, this semi-dry system has proven to be the most efficient technique for visualizing polycystin-1 by Western blot. And a few other things that we're going to need for the gel. We're going to use lithium dodecyl sulfate sample buffer. It's from Invitrogen. This is 4 times. Because things like beta-mercaptoethanol and DTT smell so bad, we use a non-smelly alternative called TSEP, which is a very good reducing agent. And the molecular weight markers we're going to use are high mark, because we're really looking at some big proteins here. Polycystin-1 runs, well, the ectodomain runs at 450, and its C-terminus runs anywhere between 130 and 150. And we're also going to use Novac's sharp pre-stained protein standards as well. So we're going to run 2 molecular weight markers at the same time. There's a few other things that we're going to need. We're going to need a chemiluminescent substrate, and I make my own because I think it's actually better than the commercial. And so I use luminol, p-coumaric acid, and hydrogen peroxide. And if you order these guys, you'll have enough to keep you going for many, many years. You're going to need some dimethyl sulfoxide to dissolve them. And the secondary that we use, which is cognate, that means recognizes the mouse IgG1, is from Southern Biotech. It's a 1070-05, and this is conjugated to horseradish peroxidase. So the luminol, p-coumaric acid, hydrogen peroxide is actually the substrate for the horseradish peroxidase. Now, from equipment point of view, I use a DCX700 gel box as a very useful and robust gel system. We're going to use the transblot turbo from Biorad to actually transfer the gel onto the nitrocellulose. And the imager we're going to use is an Amersham Imager 600 or an AI 600. And the buffers that we're going to use, the running buffer we're going to use is a 10 times tricine running buffer. It contains tricine and trace and 1% sodium dodecyl sulfate. And the standard buffer that we use for dealing with all the blots is a 10 times TBS tween. So that's basically or 1 mole of trace, 440 grams of salt. And then if you add 70 mils of concentrated HCl to that, that'll bring it to about pH 7.4 to 7.6. And then we add 25 mils of tween, and that goes into 5 litres of water, and that'll keep you going for several weeks. Now, to make the blocking milk, we use TBS with 5% milk. So we dilute this 10 times down to 1 times, and then for every 100 mils of TBS that you add 5 grams of non-fat dried milk, and we get ours from Hy-Vee. And then whenever you're using an antibody, we like to dilute that further, 1-to-1 with TBS again, to give you a final concentration of 2.5% non-fat dried milk. So this was a tricky technique, but I think we've ironed out many of the problems with the transfer and with the detection. And so now we'll go to the lab and we'll set up a gel and transfer it and then detect it. And then at the very end, I will discuss the proteomics and the Westernology, really, of the polycystin protein. Hi, we're going to do a Western blot today, and we're going to do it for polycystin-1, which is a big protein. So we're going to use 2 different molecular weight standards. One is the sharp pre-stained molecular weight marker from Invitrogen, and I'm also going to use a high molecular weight protein standard, again from Invitrogen, because we're looking at a really big protein. We're going to look at wild type RCTE membrane prep, clone H, which is polycystin-1 null membrane prep, exosomes from the 2, okay, here, and then exosomes from 2 individuals that are normal, okay, but these exosomes come from their urine, okay. So the first thing that we want to do is take 60 microliters of each of these and 20 microliters of this mix here, which is 4 times blue juice, which is made up by taking 450 microliters of 4 times blue juice and 50 microliters of bomb breaker T-Sep. Okay, so I'll get on and I'll make these up right now. So I just aliquoted out 60 microliters of each of the membrane preps and the exosomes from the cell culture system and from urine, and now I'm going to add 20 microliters of the 4 times blue juice that's got T-Sep in it. And so T-Sep is a non-smelly reducing agent. Okay, it's a very, very good one. So I'm just going to add 20 microliters of T-Sep to it, and then we're going to cook it for 10 minutes at 65 degrees. So let's just quickly do that. Oop. 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 So that will bring us up to about 80 microliters of sample. Now we're going to load these twice, and we're going to use about 30 microliters each time for the membrane and the exosomes. And we're going to go down with the urinary exosomes because they're very rich in polycystin-1. We're going to use about 10 microliters of them. So this is just a ranging experiment to see how well these work. And also I'm testing out a new batch of 7E12, which is the monoclonal antibody we'll be using here to detect these. And so we'll just do a very simple experiment where we'll do this in duplicate on two different gels. If you can see what I'm saying, right? So you take these, and we're going to give them 10 minutes on a block at 65 degrees. So here we go, 65 degrees, 65, and we just go boop. Now you don't cook your molecular weight markers, obviously, okay, and then you want to give 10 minutes. So now we're going to set up a gel, and we're going to use these Novex 3-to-8 tris acetate gels. We're going to use 2 of them. I'll just show you how to set something like this up. You take out your 2 gels, put this back in the cold room, and the important thing about it is you want to take out the wells and you want to take off the seal. So you just open like this. Take the wells out. Like that. And you've got a comb. And then take the bottom tape off. This is really important. It's a real newbie mistake is to not take this off, because you need to make the contact. And sometimes you just need a knife just to get in get it started. There you go. There's one. And here's the other. Just open it up. Right. Take your comb out gently. Like that. Take your knife. Take the white paper off the bottom. Take the white paper off the bottom. Oh, come on. I find it very difficult with the gloves sometimes. Right, so you got 2 of these. Good. Now you need a gel box, and so we'll just grab a gel box. So here's a gel box. Just take away the white cup, or the white rubber. 1 gel box, and then what you do is you undo these clips. There's a buffer dam at the back, usually. Though not in this case. Yes, in this case. Like that. And you've got 2. You've then got 2 slots. See, here at the back. So you put your first gel in at the back. Slots in like this. Bring it in. Clip it. Clip it. Okay. Second gel. This. Clip it in. Now remember, the high bit is facing the outer buffer tank. This is the inner buffer tank. Clip it and then clip it. Okay, so you've got an inner chamber and an outer chamber. And the name of the gel box is it's a very standard Invitrogen gel box. Oh yeah, here it is. It's a DCX700. Okay, so you've got this set up. Okay, now here you've got a buffer which is 1 time, so this is a 10 times buffer here, which is tricene and tris with at 1%. So that's a 10 times buffer. And what we've done is we've made up a 1 times buffer here, which we will first fill the back tank with. And then put the rest in here. Fine. There you have it. Give it guys ready to go, and we've got 4 minutes 20 seconds to go. So what we can do is we can get our molecular weight markers on. So the first thing we're going to do is we're going to put on our Novex molecular weight markers. These are really good molecular weight markers. They're rainbow, and they're sharp, pre-stained. Okay, come highly recommended actually. And I think I'm going to go for a 20 microliter pipette for here. And what we're going to do is we're going to load up. And so let me show you. Come down you look at your gel box. And so you load just 10 microliters, and got exactly 10 microliters for the back one now. Like that. Okay, good. So that's the first one done. So now I'm going to load the gel with the samples, starting with the wild type, and do it twice, like this, and then like this. Okay, and we've got a little bit left over, so we'll go down to 10. Just to top it up a bit on each side, and this, and then like this. Easy. And then we'll carry on and do the next one, and then we'll stop for a bit, and then we'll start again when it's time to run. So that's fine. So we're ready to go. Now what we do is we put the lid on, and it's negative to negative and plus to plus, of course, like this. And then you switch on your power pack. And you want to give it 150 volts. Oops, we'll short there a little bit. And for 1 hour. Okay, and then press run. Now when you come across here, you see there's a curtain of bubbles at the back, and that's exactly what you should see. Okay, so the liquid level here is right to the top on the inside and about here on the outside, and all the current is now going through the gel, and in a few minutes you'll actually see the gel, the blue dye going into the gel, and some of the molecular weight markers resolving. So we're just going to leave that on the bench for 1 hour, and it'll run out quite nicely. And we can go for a coffee, or you can do something else. I'm going to go and do something else right now, and then we'll be back. Okay, good. Okay, we're about 14 minutes into the run, and you can see that the blue is just under the water level on the outer tank, and it's running quite nicely. And we'll come back in about half an hour and have another look. Okay, we're about 30 minutes into the gel here. You can see the leading dye edge, molecular weight markers, you can just about see them. The Novex, the Invitrogen Sharp, and then the high mark. Okay, so it's running nicely. Okay, now we're about 45 minutes in, and you can see the gel front, and now the molecular weight markers are much clearer here, so things are going good. Come back and take it apart in about 15-20 minutes. Okay, we're now about 1 hour and 12 minutes into the gel, and as you can see, it's gone right down to the bottom. You can see the molecular weight markers. So we're going to take this apart. So I'll just hand this off to Andrew. Could you get that? Right, so I'm going to just turn off the power supply, take off the lid, and get some gloves on. And so this is how it looks. What we've got is 2 gels, and we're just going to open up and open up. Close out. There you go. Along the bottom, and the molecular weight markers here. Here. Molecular weight markers on the bottom. Let's take that out. Get that out. Both duplicates. And take this away. So now we make up a solution that is basically, this is 5 times trans blot buffer. So you use 100 mils of this, 100 mils of ethanol, and 300 mils of water, milligauge water, and you have your transfer buffer. Okay, so the transfer buffer goes into a tank here, like this. And then you take some papers like this and soak them in. So this is from a kit, and the kit is one of these, a trans blot turbo kit, okay? And so we're just using its transfer buffer and the papers that come with it. And we're going to also use one of these, which is a transfer setup for a biorad transfer system, which we'll use in a second. Put these over here. So the first thing we've got to do is open the gels. Take a gel like this, crack it on the side, and crack it on the side. Okay, and crack it like that. Okay. So I like to open them up first of all and trim them like this. So they come out like this, and then, as you can see, there's this a kind of pedestal down here that you can pick the gel up with, like this. And you've got the wells at the top. Now, one of the tricks is to remove the wells, because they can lead to dirty blot. Okay, because there can be residual material there. So just cut them off, put them in the bin. Cut them off, put them in the bin. That's one. And do your next gel so they're ready to go. Crack them open. Crack it open. Get it in there. Okay, up. Biorad gels. These are Invitrogen gels, sorry, not Biorad. Okay. Again, you've got that pedestal you can pick up with. Get rid of the wells. That's the most important thing. Put them in the bin. And this is an Invitrogen tool. I think it's from Oriental Cooking. I've never used one in the kitchen, but it's very handy when you're doing Western blots. So you take your gel transfer system, pick up your blotted papers, stick them down like this, so they're immersed in the transfer buffer, and just now we've got to get rid of any crinkles or anything like that, so you just smooth them out like this. Now the next step is to get the nitrocellulose. So the nitrocellulose comes in the kit, and this is the best. So we use nitrocellulose because it seems to be the best for polycystin-1. And you have two pieces of paper on either side. It's the stuff in between that you want, which is nitrocellulose. And interesting thing about nitrocellulose is it's gun cotton. It's basically used to be used in bullets and shells. It's actually quite flammable. So here we go. We'll pop it in like that. Immerse it. That's great, it's ready to go. Now the big trick is no bubbles, okay? You don't want any bubbles in this situation. So you lay nitrocellulose like that and you smooth out any bubbles. So rule number 1 is no bubbles, and rule number 2 is no bubbles. So I pick up using the thick bit of gel, and have the thin bit, 3% just behind it, and I smooth it down like this and leave this off the end like that. Okay, then pick up the next one like this and pop that down like this. Now we've got to do a little bit of trimming. Again, no bubbles. Bubbles are your big enemy here. They can ruin a really good gel. So just now what I like to do is then cut off these kind of pedicels at the bottom, sort of thick bit of gel. Take it off and take it off like that. So right now, so the order it goes is paper, nitrocellulose, gel, and then we need to put more paper on top. Okay, so we've got that, and again, no bubbles. Get rid of the bubbles. Gotta be a bit neurotic about them. Yeah, that's lovely. Okay, now then, what we're going to do is get another sheet of batch of those papers here from the kit. Immerse them in the blocking buffer, in the transfer buffer, sorry. This. Okay, that's ready to go. Pick it up, pop it on like this. Okay. No, again, no bubbles. It's probably rule number 3 now, no bubbles. So, okay. And then pop this on top. We've got a lid here now, and the lid goes on like this. Press down, turn until it locks in on all sides and it clicks. Good. Right, now the most important thing is then to pour off any excess like that, and then now we're going to transfer it. Okay, so good. So here we're going to use a trans-blot turbo system from Biorad. Okay, and basically we're going to turn it on at the side, and here we have our cassette that we were working with earlier on. Again, we're going to slot it in here. Now then, we've got the critical thing here is what program are we going to use. Okay, so I go list, I go Biorad, I go with 2 mini gels or 1 midi. This is what we're going to use that one. And then I like to use the high molecular weight, and I edit it. Okay, and what I like to do is I like to change the time, and I give it 14 minutes exactly. Okay, so this works really well for polycystin, and then you press OK, and then you press run, and then you run on A and put it into the A slot here, as you can see. And there you go, it's running. So we're getting about 2.5 amps, 21 volts for 14 minutes. So it's quite a bit of power. It's about 55 watts or something like that. Okay. So let's leave it for a bit, and then we'll come back. So this is just coming to the end right now. As you can see, we're almost there, and it should be stopping any minute now. There we go, we're complete. Okay, so you just pull your cassette out, and actually it's quite warm to the touch. You can put your hands on it, it's warm. Switch this off, and always be careful to cover it up. We'll just do that. Just because it's a valuable piece of equipment, and I don't think good Westons for polycystin are possible without it. I've tried multiple other systems, but this is the best. Okay, so back to my lab. Right, so we're going to open the box and see if we've got a good transfer. Just clicks open like this, and you just pull, and it kind of just falls apart. And what we've got here is the actual gel is like this. See that? And we've got to get it on the other side too. It's still quite warm, and sometimes it sticks a little bit. You've got to be careful about that. And go like this. And put it off again. Sometimes it tears. that's okay. I'm going to lay it in the box here and pull off the rest of the gel. And I usually just use a scalpel to pick it up again. It's probably better to pick it up from the small side. This sometimes happens, that the gel breaks, but it's not important because we just want to get rid of it. Okay, like that. And there's some little bits in the middle, but they're not going to be that important because we're actually going to cut them out. We've got to cut these two gels apart. One we're going to freeze and the other we're going to keep. So I'm just going to take a razor blade down like this, straight through it, so we've got them both cut. Now, when you look at this fella, you can see you've got your high molecular weight markers here. This guy is about 260. This is about 500. So, nice gels. So one thing I do like to do is stain them Ponzo S. Ponzo S is a food dye. It's a very, very quick way of actually seeing how well you transferred. And so I just take this, it's Ponzo S, 0.1% and 5% acetic acid. And just pour it on top. And basically you do it by eye, okay? You just look at it. And you can see already, I think, that there's proteins there. And it gives you a rough idea of the loading. Just do that. And, well, yeah. We've got 2 lanes here that are looking pretty good at the moment that have got membrane protein in them. But the exosomes are, you can hardly see anything because there's not much protein in them, okay? So what we'll do is we're going to wash this with distilled water. So I'm going to pour this off into the sink, wash it with distilled, wash it with distilled, and there you have it. And so if you look now, you've got your wild type membrane, your clone H, polycystin negative membrane, you have your wild type exosomes, and you have your exosomes from clone H, okay? And then here you've got your urinary exosomes. You can see here there's 2 Tam-Horsfall bands. I'll just give it another quick wash. You see it's very dynamic here. You're just having a quick look. See, yeah. So now you can see those 2 Tam-Horsfall bands, you see? Bang and bang. Okay. So we've got a lot more clone H exosomes than we do wild type. And this is about the best way of looking at your loading. And you can come back at some point and ask the question, you know, if I want to get the loading perfect, how much do I reduce my loading by or not? So have another quick look at that. Let's bring it into the light for a second. Yeah, you can see again. So wild type, clone H, wild type exosomes, clone H exosomes, and then the 2 urinary exosomes. And this is Tam-Horsfall, okay? Okay, and I'll do it once more. There you go. That's a better view. So wild type, clone H, exosomes from the wild type, exosomes from clone H, and the 2 urinary exosomes. So that's great. Gives you a rough idea of how well you've loaded. Now then, what I then like to do is I pop it into a large container like this, like that, and then add milk. So this is 5% non-fat milk in TBS tween. I'll talk about that in a second. You just pour it on top. Be quite generous with it, okay? So the TBS tween, the 10 times solution is here, okay? So it's made up by having 121 grams of trace, well, 1 mole of trace, 440 grams of NaCl, and 70 mils of concentrated HCl, and 25 mils of tween 20 in 5 liters of water, and you mix that up, and that's your 10 times. So you dilute that to 1 times, and in this case where we've got the milk, we add 5 grams for every 100 mils that you're making. So if you're making half a liter, you use 25 grams. So we just pop this like this, close the box, and then we take it over here and we'll move these guys. I don't need them anymore. And we have a shaker. We just shake for about half an hour. like that. Maybe a bit faster. Okay, fine, good. Yeah, and for the other half of the gel, we just put it in a plastic bag like this and add some water to it. Like that. And we're good. And it's good to freeze, okay? Okay, so now we're at the stage where we're going to use a monoclonal antibody. Here it is here. And it's, as you can see, it's 7E12 and it's about 0.9 megamil, almost 1 megamil. Okay, so 7E12. So what we do is we're going to make this, dilute this in 1 and 2,000 into 2.5% milk. So we have 5% milk here, and this is TBS tea, tween, 25 mils. So what I'm going to do is just dilute this 5% down to 2.5%. Okay, there you go. So it's 50-50. We call it 50-50 milk. And then we're going to use the antibody at 1 and 2,000. So here's your antibody. So for 50 mils, that will be 25 microliters. So let's get a pipette for 25 microliters here. So we should have had this to hand. That's not very good. How was that? Ah, here we go. Got the right one now. 25. Okay. And we grab and just I'm looking at it for the camera here. There you go. 25. 7E12. You just pop it in. 50 mils. Alright. Done. Mix a couple of times. Then we'll go over and we'll have a look at our gel. Our blot now, actually. And you can see the milk's gone slightly pink. That's the once the S coming off. So just chuck that down the sink. It's done. And one last quick look at the gel. You see how the poncer has come off it. It's quite a handy food dye, that. And you add your 7E12 to it. Okay. Alright, so it's sitting in there now, just like this, and we are done. So now we have to put this at 4 degrees overnight. So and as you can see, it's shaking back and forward. I don't know if you can hear me over the fans, but there it goes. And we'll leave that overnight. Right, so this is the Western from overnight. It's been in 7E12, 1 and 2,000 in milk. It's floating around in there. First thing to do is to get rid of the milk. Pour that down the sink. Okay, and then quick wash with TBS. And just give it a quick rinse. The Scottish word is dicht. And then another one. And then we're going to give it 5 minutes, and we're going to give it 3 5-minute washes. Okay, pop them on like this. There you go. Fine, we're done. So again, we're going to make up the secondary, which again is putting half and half milk. So 25 mils of TBS and top it up to 50 mils with milk. Like that. Give it a quick mix. So this is 2.5% milk again, right here. Then what we're going to be using is goat anti-mouse IgG1, okay, human absorbed HRP, all right, and the code number for that is Southern Biotech 1070-05. Great antibody, works every time. So we're going to use this at 1 in 2,000. Now you might be able to get away with less, but and again 25 microliters. Set it up. Looks kind of brownish. That's the peroxidase. It's got a heme group in it, hence its colour. Pop that in like that, up and down, and mix it, and that is ready to go. Put everything else away in the cold, and we're good. Okay. Oh, okay, we've given it 3 5-minute washes. Okay, and you can see it's nice and clean. There's no milk there whatsoever. So pour that off, and then we take our 1 in 2,000 anti-IgG1. 7012 is a mouse IgG1 antibody, so this is anti-IgG1 HRP conjugate. Pour it on top like that, and then we just leave it there for at least an hour at room temperature. It can be a little longer, but an hour is about the minimum. And then we'll come back and then give it 3 more washes, and then we'll detect using a chemiluminescent substrate. And we'll actually use a homemade one because it's actually better than commercial ones. And I'll let you into how to do that. Okay. So, okay. Now we're at the stage where we're going to do. We're just finishing the secondary. So there's an anti-IgG1 HRP on this. Okay. So we're going to just pour off the milk, and then give it a quick wash like this, and then a 5-minute wash like that, and that's it. Put it back on there. Okay, now we've finished the third wash, and we're going to detect. And instead of using a commercial chemiluminescent substrate, we're going to make our own, okay? And this is nice and cheap. So the first thing we're going to use is pH 8.5, 0.1 molar trace, okay? Make sure that's nice and mixed up. We want 12 mils of that. 12 mils. Right here. Then we need to get a pipette. And the first thing is we're going to add 26 microliters of p-coumaric acid. Put this back on top. So the p-coumaric acid is at 15 mg a mil in DMSO, and we'll keep it protected from the light. There you go. You pop it in, it goes transiently cloudy, and then it's in. Give it a quick mix. Then luminol, and you want 60 microliters of luminol, and that luminol again is in DMSO and at a concentration of 40 mg a mil. Again, keep it away from the light, but it's alright at room temperature. Lasts for a long time. And then put it into your substrate. Good. Give it a quick mix. And then finally, you want 30% hydrogen peroxide. Just be careful with this, you're going to need gloves. And you only need 3 microliters of it. So let's get a small pipette here, and 3 microliters. Now put it on the side of the tube until I need it. because as soon as you add it, it becomes a complete mix and it's ready for the substrate. So just take 3 microliters, just a little bit of hydrogen peroxide. Okay, so this is a lot cheaper than the commercial forms that you can buy, and it's better, I think. That's why I went across to it. Okay, now we're going to go to the machine with our blot and with our substrate, and I like to just keep the hydrogen peroxide as a little droplet there. Okay, you can see it there, and we'll mix it in once we get to the machine. Okay, so that's fine. So now we're going to detect using this machine here, which is Amacham Imager, or AI 600. Okay, and as you can see, we're going to do chemiluminescence with a colorimetric marker, and we're going to go auto. All right, just like that. So then we come here, and I just grab the blot and stick it onto the tray like this. Okay, and as you can see, here's the sharp Invitrogen markers, and then the high mark. You can see we've split the 2 second and third. That's a very good sign that the resolution is very good. And then I just pour the substrate on top, mix it and pour it on top. Okay, and then we're ready to go. I don't wait. I just go, make sure it's nice and even, and I pop it in the machine here, the top. And okay, we're just going to press start now. It's cooled down, and we just go start, and then it accumulates, gives us an exposure first of all, auto exposure. Hopefully it's 1 or 2 minutes. 2 minutes, that's good. And so it's probably got an exposure about 1 minute here. So we just wait. Okay, now I'm just going to put the key in the machine. Get the right way around. So we're going to collect data off it. Now if we go to the screen now, we can see our molecular weight markers, and then here we've got the trunk PC1, the NOH sensitive form, which is in the ER, in the mature form, and you can see here in clone H you've got a lot of the ER form. Okay, and you've got a lot of the ER form in the exosomes from clone H. It seems to be getting out. And then these are the 2 urine samples, exosomes. So what we'll do is we'll stick this at the end of the presentation so that you can look at it again. So we're just going to save this, and you just press save, and then we don't want instrument, we want USB, and we'll call it something sensible. It's actually to test a new batch of 7012. Okay, and so we'll just say done and save. Hi, so we've just completed a Western blot for polycystin-1, but to really understand it, we've got to understand how polycystin-1 is cleaved up and how it is glycosylated. So the first thing is that polycystin-1 has a signal peptide, which means that there's a large ectodomain which is extracellular, and then the protein then winds through the membrane 11 times and then terminates. The whole thing is 4,302 amino acids, and it would weigh in around about 550 to 600, and sometimes you can see that on a Western blot. The antibody we're using is 7012, and it's an antibody I suppose created in the late 1990s to bacterial recombinant protein that encompasses the cysteine-rich N-terminal, the leucine-rich repeat, and the C-terminal of the leucine-rich repeat cysteine knot structure at the N-terminus, extreme N-terminus of polycystin-1. Now we screened this on an FC chimera, which was made in COS7 cells, which encompassed the same region. And we got a couple of monoclonals, but 7012 was the best, and it's an IgG1 kappa. So it sees the whole of polycystin from this end. And so sometimes you can see the full-length protein at almost 600 kilodaltons. Now the protein undergoes a GPS cleavage event at position 3048. It autocleaves itself very early on in its maturation in the ER. And from this you get two forms. You get an immature form that's in the ER and is endo-H sensitive and tends to be the smaller band. It is about 430 to maybe 440 in size. There's also a mature form that's moved out of the ER and has gone to the Golgi or past the Golgi and is now on the primary cilium or on the plasma membrane. And it weighs in round about 450 to maybe 470 kilodaltons. Now in humans, and I suppose the higher primates, there's a shorter form called trunk PC1, and it's generated because intron 21 in polycystin has a very long polyprimidine tract, all C's and T's, for about 3 kb, and splicing across it is very inefficient. And so what happens is you tend to get translation termination around about intron 21, and the product is about 310 to 330 kilodaltons in size, and it's glycosylated, but it always has immature ER type glycosylation, endo-H sensitive. It's never mature. And so we really should see four forms. We should see the full-length form, and then the mature form under that, and then the ER form under that, and then the trunk PC1 form under that. So let's have a look at our Western blot and see what we've got. So the first thing is that we just want to check that it's run well, and so we've got the high mark molecular weight markers here. So this is 460, and this splitting here of the second and third bands is a good sign. It means that we've got high resolution gel here. So it splits this 268 from 238 kilodalton band, and this is 160. So when we look at the wild type membrane, we should really see the full length form here, but we don't really. It transfers very poorly, and only occasionally do you see it. The top band is the mature form, and in here it's running about 470. Classically, it's meant to run at about 450. And then under it, we have the immature form. In this case, this is running about 430, 440. And then under this, we have the trunk PC1 form. Now, clone H has a transposon inserted in the second last exon. That's transmembrane 11 in polycystin-1. And what you can see here is the ectodomain accumulates in the ER form, the endo-H sensitive form here. You've got human trunk PC1 here, and you have got a very, very small amount of mature material here. Now when we look at the exosomes, we've got the wild type exosomes and the clone H exosomes here. Now by accident we loaded a lot more clone H exosomes than wild type. If we were to redo this, we would reduce this maybe tenfold and keep the wild type loading about the same. But here you can see there's a very faint mature band here. And in the clone H, we've got exosomes that are popping out here that have got the ER form of polycystin-1 on them. That's an interesting observation in itself, and we'll have to firm that up a little bit. Now, the two urine samples have got mature polycystin-1, and if you track this across here, you can see it lines up quite nicely with the mature form in the wild-type membranes from the RCTE cells. So that's polycystin-1 Western blot, and that's how to do it. Now, I have a hypothesis that people that have polycystic kidney disease tend to have less polycystin-1 in their urine, and I think we've shown that. There's also this idea that that if you have small amounts, if you have the disease and you have only small amounts of polycystin-1 on your exosomes, then you tend to have bigger kidneys. And so this is something that we're investigating at the moment. And in order to do this, we really need to have a perfect and robust Western blot. And so this is one of the reasons I presented this, to give people a good idea of how to do one, and so that they can follow up some of the work we've been doing on this. So that's how to do polycystin-1 Western blot, and now over the next few years we'll probably perfect this a little better. We might use the LICOR system, for example, to image the Western blot, or perhaps a new technology will come along. But at the moment, this is probably the better way of looking at polycystin. And so with that, I'll just sign off. Okay, and thank you for listening.